Hello everybody, in this lecture we will be solving 2017 AMC 12B problem number 25. Here is a view of this problem. Make sure you spend some time trying to understand what the question is asking, especially this curious fact, which is like almost a riddle. It took me several readings until I really understood what the question was actually asking. But you have n players, obviously. Oops. Sorry for that. And if you need to pause the video, just go ahead and pause it and make sure you understand it first. So you have n players, they are participating in a tournament. However, well, obviously each team will have 5 players. So one team consists of 5 players. So you choose 5 players and they can register as one team. But not all 5 player subsets will be a team, right? So because otherwise then we would have and choose 5 teams, which is not necessarily the case. Let's assume that we have T teams. Okay, so we have T teams, we have n players and T teams registered. Now the interesting thing is, like you guys guessed, you can have one player be a part of different teams. So the same player can register himself to multiple teams. However, not the same 5 people can register 2 separate teams. At least one person from that team should have to be different, right? So 2 teams will differ from each other by at least one player. Okay, now let's come to that curious fact. So the question is talking about the following. So we need to calculate an average over all subsets of size 9 of the set of n participants. So consider all subsets of size 9. Obviously there are n choose 9 such subsets, and because the question is asking for an average, so therefore we are interested in the first average. So let's call it average, because it consists of subsets of size 9. Let's call it average 9, or how about that, let's call it A9. All right, so A9 is the average over all subsets of size 9. Because we have in total n choose 9 such subsets, that would be the denominator, right? Because we are taking an average. So we are averaging out n choose 9 numbers. But what are these numbers that we are calculating? So the number of complete teams whose members are among those 9 peoples. What? Okay, the number of complete teams, so whose members are among those 9 people. So what you do is the following: you pick from these n players, you pick a subset of size 9. So you pick 9 players and you count how many teams are registered in the tournament from any 5 of those 9 players, right? Obviously there is 9 choose 5 max. The max can be 9 choose 5. Every 5 element subset can be a team, and so the max number that you can enter here would be 9 choose 5. But most of the time it will be much less than that, right? So not all 5 player subsets of that subset of 9 players will be registered as a team. And then you pick another 9 player. So you got your first number, plus you pick another 9 player, you get another number, and you pick an, okay, so you will have in total n choose 9 numbers, and then you divide by n and choose 9, and you get your A9. And pretty much the same thing will happen with A8. We will calculate a number called A8 with the same logic. So n choose 8 among all subsets of size 8. You randomly pick 8 players. You see from how many teams are registered from the members of these 8 players, but all the team members should be in of that team that we want to count should be among these 8 players, and you count that number plus, and then you pick another 8 players, and so on. Okay, so does that make sense? Well, the answer should be no. Okay, so let's think a simpler example. Okay, so consider this simple example. Consider we have in that tournament, we have, say, 6 players. Player numbers 1, 2, 3, 4, 5, 6. Okay? And let's say that the following teams are registered in the tournament. Let's say the registered teams are consisting of team 1 is consisting of players 1, 2, and 6. Team 2 is consisting of players 2, 3, and 4. Team 3 is consisting of players 3, 4, 5. And finally, team 4, we have 4 teams registered, consisting of players 1, 4, 5. So you guys understand the game. We have 6 contestants, 6 players, and each team has, one team has 3 players, right? Does that make sense? I'm changing the numbers so that we can work with some concrete numbers, and so this way it will be easier to understand that previous problem. Okay, so each team consists of 3 players, and apparently we have 4 teams registered for the tournament. Now let's calculate the following. Let's say that we change the problem, and the problem is the average of, say, 5-player teams. Okay, so we want to calculate A5. So A5 in that case would be n choose 5. First, let's look at all 5-player subsets. And obviously, luckily there isn't too many, because in total we have 6 players. So the 6-player subset, the 5-player subsets are 1, 2, 3, 4, 5, 1, 2, 3, 4, 6, 1, 2, 3, well, not 3. Oh, no, yeah, 3, of course, 5, 6, 1, 2, 4, 5, 6, 1, 3, 4, 5, 6, and finally 2, 3, 4, 5, 6. Does that make sense? Now, in the numerator of this expression, I will add 1, 2, 3, 4, 5, 6 numbers in the following sense. First, let me count how many of these teams are totally included in each of these subsets. Well, inside this subset 1, 2, 3, 4, 5, only 6 is missing here, obviously. So this team cannot be there. This will be there, 1. This is also there, 2. This is also there, 3. There will be 3 teams here. Does that make sense? This one will count 3 times. Next, this one, the second one, it has 5 missing. So therefore, this one is good, 1, 2. These 2 are not good because they have 5 in it. So this one will contribute 2 to the average. Plus, next one is missing the 4. No 4, so 1. That's not good, not good, not good, because each of these 3 have 4s in it. So we have only 1 good. Next one is missing a 3, 1, 2. 2 good sets here. So we will count 2 times. And then this one is missing a 2 here. So this one is a 2, this one is a 2. The last 2 don't have 2. So we will count this one 2 times. And lastly, the last one doesn't have a 1. So therefore, these 2 are contained in that subset. So we have 2. That's it. So we have 3 plus 2 plus 1 plus 2 plus 2 plus 2. So in total, we have, the numerator is, I assume, 12. I guess it's 12. And 6 choose 5 is the same as 6 choose 1 divided by 6. Oh, that desired average is just 2. Now, did you like it? Yeah, probably you didn't, right? So, well, we were able to solve this because we know what our numbers are concrete, 1, 2, 3, 4, 5, 6. But the problem we have n players. And that n is not known. In fact, the question is asking for n, right? So we need to find another way to count this sum here. The denominator is obviously cool, right? So I don't want to change the way the number of subsets. I know there will the number of subsets here is clear, right? We have 6 choose 5 or 6 subsets that I'm averaging out, but there must be another way to make that sum the total, right? To count that total. And this is, yes, there is another way. This is kind of, I'm trying to come up with a counting in 2 ways type of argument here, right? And here is the deal. Okay, here is the crux move of the problem. The crux move is to count in a different way. And the best way is, rather than looking at this subset and looking at each of these 5-element subsets and then finding how many of these subsets are included in this 5-element subset, I can do the opposite, right? I can focus on each team, and I can count how many 5-element subsets will include this team. Does that make sense? I hope so, right? So you can pause the video here and then you can quickly do the count again, right? So that's cool. So 126, is 126 included here? Of course not, because this one has a 5 in it. Is 126 included here? Yes, 1. So the 126 is not included in the first one because this one has a 6 and this one does not have a 6. Okay, is 126 included here? Yes, 126. Yes, 1. So is 126 included here? Yes, 2. 126 yes, 3. 126 no, because this doesn't have a 2. This one no, it doesn't have a 1. So we have only 3, right? 126, 126, 126. We have 3. Aha! That's super. But interestingly, we will only end up adding 4 numbers. It doesn't matter. The denominator will still be 6 choose 5, right? So it doesn't matter. All I do is I count the numerator in a different way. That's it. In fact, I can even do faster than this, right? So for instance, 2, 3, 4. You can guess what the answer will be. It will be 3 again. The other one will also be 3. Why is that? For instance, let's quickly check 2, 3, 4. Here 1, here 2, and here 3. How do I know I would get 3? Very easy. Well, because we already have, let's start for instance, let's have a look at 2, 3, 4. Okay, so let's have a look at this one. We have 2, we have 3, we have 4. Well, for 2, 3, 4 to be included in any one of these 5 element subsets, I need to attach, there must be 2 more elements in that subset, right? How many ways can I choose these remaining 2 elements? Well, how many other elements left? So we have 3 more guys. 1, 5, and 6. So therefore, we need to pick 2 of these 3 guys to go into this set, right? Order doesn't matter, right? So these are obviously team members. So there is 3 choose 2 ways, and that's 3. Oh, so that's why we keep having those 3's in here. And 3 plus 3 plus 3 is 12, and we get the same answer. Aha! That's the crux move of this problem. So let's go up now, and let's kill this monster. So, going back, so we have okay, so we have all these subsets of size 9, right? And all I will do is, okay, so let's have that subset of size 9. So this 9-player subset. Well, I want to have my 5 players. Okay. So we have T teams, obviously, right? So we need to count each of these T teams, right? Each of these teams will appear in how many of these 9-player subsets. So whenever you have a team of 5 elements, 1, 2, 3, 4, 5, so check, how many of the 9-player subsets will include that team, like we did in our exam? We need 4 more guys, right? And obviously this is unordered, so let me put commas here, so order doesn't matter here. I need 1, 2, 3, 4 more guys, and those 4 guys will be selected from among not n players but n minus 5 players, because 5 of the players are already chosen. So from among the n minus 5 players, we'll go ahead and we will choose 4 more guys. So, and because so therefore each team is counted this many, it will be counted in this many of the subsets, but because I have T teams, I will multiply it by T, and that's it. I'll do the same trick for the other one. So 8 element subsets, so therefore 5 of my guys, 1, 2, 3, 4, 5s. How many more players should I add? 3 more guys. From among n minus 5 players, I pick 3 more guys, and each team is counted in this many of the subsets. Because I have T teams, I will multiply this outcome with T. Now we are told that A8 and A9, these 2 numbers, are reciprocals of each other. So therefore, when you multiply these 2, they should give you a 1. And now that we can, oops, do I have space? Okay, let's do it here. So therefore I have, and this is, by the way, the official solution, right? So n minus 5 choose 4 T over n choose, was that the case? Yes, n choose 9 times n minus 5 choose 3 T times n choose 8, sorry, divided by n choose 8 is equal to 1. Okay, I'll leave the Bashi calculation algebra to you. This thing, when you compute, should come out as the following, a very nice expression. Well, obviously you need to do a lot of clearing and stuff, but it's not that bad, so you can do it. So it is n times n minus 1 times n minus 2 times n minus 3 times n minus 4, all divided by I think it's 32 times 9. Well, actually these are like powers of, so this is 2 to the 5, 3 square times 5 times 7. So let me write it like this. Okay, so this is the number of teams, obviously a positive integer, right? So now the question turned into the following. The question originally was asking for how many values of n in this range, sorry, how many participants can we have? We know that there are n players participating in that basketball tournament, right? So how many possible values in this range is possible? So any value n is possible as long as it makes this expression, right, on the right hand side, an integer. Does that make sense? So n is well, obviously n is in the range 9, because we are picking 9 element subsets. Obviously we should have at least 9 players. So is possible if and only if, okay, so check this out, if and only if the numerator here is divisible by 32, by 9, by 5, and by 7, which makes eventually this integer, right? If and only if t is an integer, which is the case if and only if our numerator here, n times n minus 1 times n minus 2 times n minus 3 times n minus 4, okay, what happens to this guy is congruent to, well, it's congruent to 0 in mod 32, mod 9, mod 5, mod 7. Well, 0 mod 32, the same expression is 0 mod 9, mod 5, and mod 7. Awesome. Well, to begin with, so one of these congruences is redundant. So can you see which one? One of them is trivially satisfied. Can you see which one? Let me change my color. Oh, come on. Yes. Okay. Well, yes, you found it. This one is redundant. Why? Because obviously when you multiply 5 consecutive numbers, right? So we have 5 consecutive numbers here. Obviously one of them will be a multiple of 5, and boom. So this one we don't have to worry about. Now we need to worry about the other 3, right? So this product, let's start from the easier one. So this one I guess is the easiest one. N minus 3 times n minus 4. Under what conditions would that product be equal to 0 in mod 7? So let's start with the last one first. Well, obviously when n is congruent to, if it's 0 then it works, mod 7. Or if it is 1 it works, right? Because 1 minus 1 would be 0 and the whole product would be 0. If it's 2, 3, or 4, it works. Does that make sense? Okay, move on to the next one. So we want this product to be divisible by 9. Well, n must be, in that case, obviously 0, 1, 2, 3, 4 works. But some more stuff works. For instance, well, 5 doesn't work, right? So because 5 times, let's write it, 5 times 4 times 3 times 2 times 1, is this divisible by 9? It has only 1 3 in it. It doesn't have any other 3s, so that won't work. 5 won't work. But 6 should work, right? Because 6 is a nice number. Okay. Let's try. Yeah, oh, that's how awesome. We have 2 3s here. Of course it will be divisible by 9. 7 won't work, right? Wait, would 7 work? Yeah, it would. Yeah, it should work, right? So let's try again. So 7 here, 7 minus 1, 6. 7 minus 2 is 5, 4, 3, and of course I have a 3 here. I have another one. Yes, this one also works. and you keep investigating, you just realize 8 shouldn't work, and so on. Okay, so good. So this is the case in mod 9. Finally, n is congruent to mod 32. Oh my god. So we want this expression to be 0 in mod 32. Obviously 0, 1, 2, 3, 4 would work as usual, but more things would work, right? So we want to make this product 0 in mod 32. Well, I'll just leave it to you as an exercise to confirm that, for instance, 8 should work. Unfortunately, 5, 6, 7 won't work, but 8 should work. Let's quickly confirm it, and then the rest you will confirm it on your own. 8 times 7 times 6 times 5 times 4. Ooh. So obviously I need 5 2's. I have 2 2's here, another 2 here, 3 more 2. I have enough 2's. Okay, perfect. It turns out 8 works. 10 works, 12 works, but more things obviously work, right? So we have a long list to go. It turns out if you add 16 to this, these will also work. 16 and 19, 20, 24, 26, 28. This is the whole list of things, numbers that will work. All of them in mod 32. Maybe I should have written it on the same line, right? So, okay, let's just do it that way. Sorry, guys. I'm almost done, promise. So 16, 17, 18, 19, 20, 24, 26, 28. I think, yes, mod 32. Whew, that's torture. Okay, so how many? Let's play that game. How many? How many? Count with me. Count with me. Okay, so how many solutions do we have? Remember, our range is n is in the range 9 through 2017. At this stage, you just realize that you have a system of congruences. System of congruences warrant for Chinese remainder theorem. You guessed it right. Yes. So each of these systems should generate one solution. But first, one solution where? In mod what's that, 7 times 9 times 32, so 7 times 9 is 63. 63 times 32 I think should give you 2016. Well, isn't that convenient? Because I look at our range to all the way up to 2017. Okay, so therefore here is the deal. In the range from 1 all the way up to 2016, every choice from this list, we have 5 choices here, we have 5, 6, 7 choices here, so 5 choices, 7 choices, and then here in this whole list, I don't even know how many choices, 1, 2, 3, 4, 5, 6, 7, 8, 9 times 2, 18. 18 choices here. So in total we have how many systems of equations? 5 times 7, so we have 5 times 7 times 18, which is equal to 35 times 18. What the hell is this? 560, yes. Systems of equations. Sorry, not equations, congruences. Systems of congruences. And each system of congruence will create one solution, right? One solution in the range 1 through 2016, right? So each one will create, wait. No. Right. So each of these, yeah, that's right. So each of these 560 systems will create one solution in this range. However, I should be careful because, because n should start from 9. How many of the 560 are in the range from 1 through 8? Well, obviously 0, and then 1, 1, 1, 1, and then 2, and then 3, and then 4, right? So 4 of them for sure. Sorry. Well, 0, I already ignored the 0, right? So I have 4 of them. So 560 minus 4 is 556. However, I need to consider 2017 also, right? And 2017 falls into which one? This guy, 1, 1, 1, right? So because if in mod 7, mod 9, and mod 32, 2017 is congruent to 1, so I need to add back one more solution, and therefore, in total, we have 557 different values of n that makes the number of teams an integer value, so which is possible values for n, right? Does that make sense? I didn't even bother. I only used the existence portion of the Chinese remainder theorem, obviously. I didn't bother writing the full solution of the Chinese remainder. I don't care what are those 557 solutions, right? All I care is for what values of n does it work. And we have found that for 557 values of n, it works. And hope you guys enjoyed this video. And yeah, looking forward to see you guys in our next lecture.